Modern graphics processing units handle vast amounts of instructions simultaneously to generate impressive visual effects in real time. However, GPUs do not offer the ability to influence the scheduling of the queued workload and can only be controlled externally. As a result, GPUs are widely considered an architecture that is ill-suited for dynamic or adaptive procedures. We propose hierarchical bucket queuing to introduce fine-grained and versatile priority scheduling to the GPU. Our framework allows application developers to set up arbitrary hierarchies of bucket queues and maintaining their contents at runtime, thus enabling a wide range of priority-based algorithms to be implemented on the GPU. Previous GPU scheduling approaches usually rely on large individual queues that accept all tasks and store them until sufficient resources are available for execution. The concept can be easily extended to multiple queues, which resembles typical behavior of modern-day GPUs. However, previous work has shown the benefits of using dedicated queues that accept only specific tasks to enable dynamic workload aggregation. We extend on this concept by supporting evaluation and assignment of tasks to queues based on their priority. Furthermore, we allow free combination of the individual queue types in a hierarchical structure to simultaneously leverage work aggregation and priority scheduling. Using our framework, highly sophisticated scheduling strategies for complex tasks can easily be implemented. We now exhibit two applications where using such a design can be of practical benefit. In order to provide high quality for a limited number of samples, path tracing algorithms can employ error metrics to prioritize image areas that exhibit a lot of noise. Here we see the sampling density over time using two different error metrics as priority values for a path tracing routine in our framework. In both cases, the GPU effectively adapts to the apparent error and assigns its processing units accordingly. To enable foveated rendering for our path tracer, we combine the expected gain metric with the viewer focus. Initially, sampling density is proportional to the color variance. If we include the focus location in the priority measure, we can see that the sampling density may also increase in areas with low variance to provide high fidelity at the user's fixation point. Furthermore, we have employed our framework to enable foveated rendering in a real-time Reyes renderer to enable guaranteed frame rates. On the left-hand side, we can see the fully subdivided scene with jumpy animations, while the prioritized version runs at 24 frames per second. Although the optimized version terminates after a set timeout, it ensures fine granular subdivision in the area of interest, here simulated by the cursor. Notice how the highlights in the heart shape deteriorate with increasing distance from the cursor. In a second scene, we see the killer model being showered in Utah teapots, where we have applied the same optimization as before. Initially, there is little difference in performance between the two versions. The cursor again marks the assumed fixation point of the user. Notice how the degree of subdivision decreases in a radial pattern in the prioritized version. As the object count increases, the regular Reyes application again is unable to produce fluid animations, while the prioritized version maintains its frame rate. User interaction and priority updating works with no visible delay and produces high-quality visuals in the requested region. The apparent performance benefit highlights the potential use of our framework for graphics applications with real-time constraints and virtual reality applications.